Hi, so today we will be looking at Chapter 4, termed Fluids of MCAT Kaplan 2015. So this section is all about the physical properties of fluids. To start with, we're going to be talking about one special property called density. Now, density is defined as mass over volume. Typically you don't see questions that say, like this amount of water has this mass. Typically we have to calculate mass when given density. So how we calculate that is we take our density, which is mass over volume, we multiply it by the volume, so the volumes would cancel off to give us mass. So if we look at our original f of g equals mass times gravity, or mass times acceleration, mass times gravity, we can just substitute our mass in, or our density and volume in for our mass. So density times volume times carry the g down, that gives us f of g. So this equation gives us the weight of the water. Now hold on to this equation as we'll come back and talk about it in terms of Archimedes Principle and the buoyancy force. The next factor that we talk about when we deal with fluids is the concept of pressure. Pressure is termed to be force over area. So it's the amount of force acting on an area. Now, for the MCAT, you should know the numerical values of atmospheric pressure. So it is 100,000 pascals, which is equal to 760 torrs, which is equal to 760 millimeters of mercury, which is equal to 1 atmospheric pressure. Now, one note is when we're dealing with physics questions, we use pascals, and when we're dealing with chemistry questions, for example, PV equals nRT, or any Boyle's law, or any of that, we are dealing with atmospheric. So typically, make sure you know which units you are using. And another equation for pressure that you should know is pressure. It's specifically gauge pressure, but we'll talk about that in a minute. It is also equal to density or gravity, or let me just erase this. The density times gravity times height, z. So if we go down, and let me ask you a question. Suppose we're in a swimming pool. Let's suppose at the same height we have, let's say, a small child that's swimming, and further down there is a large adult. Now let's suppose they're swimming at the same height, or specifically the depth. So this is height. Which one do you think is experiencing much more pressure? Many people will go with the larger adult, but the answer is that they're experiencing the same amount of pressure. Because if you look at it, the pressure is going to be coming from the amount of water that is directly on top of these two. So there'll be force of the weight of the water on top of this, on top of this. So while it is correct that the larger adult is experiencing a greater force due to the water on top, the pressure is actually the same, because we take the force divided by the area, and the force divided by the area. Because the larger adult does in fact have a larger force, he also has a larger area. So if we divide that, the division should equal out. So both the small child and the large adult are actually experiencing the same pressure. And this is really a good example on how this relates to the equation, because it's density of the water times gravity. And you know, for the MCAT we're going to use 10, not 9.8. And the last factor is height. So height is the only variable that's going to affect pressure. It doesn't matter what object it is. It could be the biggest object, or it could be as small as a penny. But if it's at the same height or depth in water, it's going to experience the same pressure. Now let's look at pressure much more. Let's look at it in terms of two types. We're going to use absolute pressure and we're going to use gauge pressure. Gauge. Now let's look at gauge pressure first. Let's suppose we have a beaker. Let's suppose, it's filled with water and we have a penny in here. So this green thing is our penny. So the gauge pressure, the best way to define it is the amount of pressure due to whatever's on top of it. So the gauge pressure would just be the pressure from the fluid directly on top. And how we would do that is we would just use the equation that we learned. So we would just do the gauge pressure, so Pg, pressure of the gauge, is equal to the density of the water times gravity, which is 10, times the height. So we'll just say this is height, or z, h or z, height or z. This is how you would find the gauge pressure. Now, in order to find the absolute pressure, it's taking the pressure of everything. So on top of this water, it's also experiencing pressure from the atmosphere. So typically, absolute pressure on the MCAT will require you to take into account of the atmosphere. Take into account of atmosphere. And it might be as simple as just taking your gauge pressure. So if you find your P of G, and just adding on the 100,000 pascals. But it really depends on which unit the pressure is in. But the absolute pressure, all you have to do is take your gauge pressure and add in the atmospheric pressure. Okay. Now let's look at a couple laws first. Now we're talking about hydrostatics. Hydro meaning the water is not, meaning it's water, and statics and that the water is not moving. So the first law that we're going to look at is Pascal's law. So let me write down the formula first, or how it's going to be applied, and then it's pretty straightforward from there. Pressure is equal to force of 1 over area of 1 equals force of 2 over area of 2. So pretty much if you have a liquid in any container or whatever, if you give a pressure to one part, it's going to be spread out or displaced, and the pressure is going to be experienced almost everywhere in that situation. So the best is to draw a U-tube shape, so something like this. So let's pretend we have liquid here, like this whole thing is this red liquid. So if, let's suppose this is, this has an area of A1, and we'll just say this A1 is equal to 1. And let's suppose this is connected to a piston system, right? So you can push down. This piston is just to show that you can put a force or impart a force onto this liquid. We're just going to impart, let's say, a force of 100. So according to pressure, the pressure experienced on the left side is just 100 divided by 1, right? Force over area. Now we know it has to be equal to whatever ratio that we have on the right side. Now let's suppose, the force that's being pushed up is now 200 newtons. Now, why do you think the force increased to 200 newtons? Well, it increased to 200 newtons because we increased the diameter. This A2 is much more bigger than A1. And if we wanted to know the diameter, or the area, much more specifically, we can just do a simple algebraic expression, and to solve for x, we would eventually get x to be 2. So if you look, 100 divided by 1 is 100, and 200 divided by 2 is 100 also. So this is how Pascal's law is going to be applied. If you have a pressure of, specific 100 newtons here, it's going to be transmitted to another place which is also experiencing the ratio of 100 pascals of pressure. Okay. I wouldn't focus on Pascal's law that much as I would focus on this next Archimedes principle. Okay, so let's look at Archimedes principle. Okay, so let's suppose we are in, let's say, an ocean. And there is a box that is floating. And so we know one force vector. There's always going to be an f of g. So this f of g that's pointing downward is just force due to gravity, which is just the mass of the box times the gravitational force, right? But if we only had the f of g vector, that would mean the box, continues sinking to the bottom of the ocean, but that's not the case. The box is floating, so there has to be an upward, force that's keeping this balanced. And this is actually the force of buoyancy. Buoyancy force. And what Archimedes' principle states is that the buoyancy force is actually equal to the weight of the water that is submerged or displaced by the box. So if you look at this area, I'll actually put this in yellow. We see that about like half of the box is submerged in water. So the volume of what is being submerged is actually the volume that is displacing the water. So Archimedes' principle states that if we found out the weight, or the f of g, of the amount of water that's displaced, that will be equivalent to the buoyancy force acting on the box. And so if we remember our equation that we talked about, how to get the f of g, we said the f of g of water is just equal to the density times the volume, because density times volume gives you mass, times gravity. And just to be clear, this volume is the amount of volume that is submerged. So that is Archimedes' principle. So what this tells us is, the box is floating as a result of the weight of the water that's displaced, providing an upward balancing force that counterbalances the regular f of g of the box. So some of the questions require you to make the buoyancy force equal to f of g. So this can be written as the density. So notice that this density is actually density of the water or whatever liquid that it's in, not the density of the box. So density times volume times gravity is equivalent to mass of the box times gravity. So we're just setting the buoyancy force and this equal to one another. Just make sure that you have this concept in your head, because some problems might require you to make them equal with one another. Okay. So there's a whole section on this book on the molecular forces of liquids, such as surface tension, cohesion. Cohesion is just when molecules stick to one another. Adhesion is when molecules stick to the... Actually, I'll just draw this out. So let's suppose we have a test tube. And then let's suppose we have like water. So the logic is the surface tension is, you know, there's like going to be some force that's going to give rise to some like surface on top of this liquid, and that's due to cohesion. Cohesion is just when the like molecules attract each other, so they form kind of like a barrier. This is cohesion, which gives rise to surface tension, and adhesion is when water molecules adhere to like a surface. So these water molecules are adhering to this test tube wall. That is the concept of adhesion. This is just some good terms to know. Don't worry about viscosity. Probably not going to show up. Just understand the concept. The more viscous it is, the harder it is to flow. Comparing water to, let's say, maple syrup is going to be much more viscous. Okay, so we can get to the concept of laminar flow and turbulent flow. So laminar flow is much more straight, streamlined, smooth flow. So let's suppose we're looking at a blood vessel. And then, so if we draw vectors, so you know vectors just give you magnitude and direction. They're going to be extremely smooth. So if I were to ask you, in laminar flow, where do you think is going to be the highest, you know, magnitude of the vector? It's actually going to be in the middle, because when you get to the side of the blood vessels, there's actually going to be friction acting on it, because the liquid, the matrix of the blood, is rubbing against the endothelial cells of the blood vessels, causing friction. So the highest one is the highest vector, or the biggest vector, biggest magnitude is going to be towards the middle. And turbulent flow is pretty much when, like, you know, it just goes random. Okay. Now let's look at the concept of the continuity equation. So let's suppose we have, you know, a pipe, and then it goes down, goes to a smaller opening, and it continues onwards. So let's suppose this has an area of A1, and fluid enters this A1 with a velocity of V1. And then this has an area of A2, and fluid enters this with a velocity of V2. So the continuity equation states that if you take the area 1, A1, multiplied by V1, it's actually going to be equal to A2 times V2. So what that means is if you increase the area, you're going to, so for example, A1 and A2, so A2 is smaller than A1. So that means the velocity v2 has to increase in order to compensate for it. So if we decrease a2, we have to increase v2 in order to compensate. So just know that logic, that if you decrease the area, you're going to increase the velocity that flows through it. So what we hold constant is the concept of flow rate. So if we look at this in terms of units, we know area is just meters squared, and velocity is meters per second. So it goes to meters cubed per second, and that's just volume moved per second. So what this is telling us is the amount of volume that is being moved per second remains the same, no matter how we decrease the area or change the velocity. So that's referred to as conservation of the flow rate. The last really important thing that you should know for this section is the concept of Bernoullis Equation. Now you should probably memorize Bernoullis Equation. I'll teach you a good way on how to better memorize this. So we know pressure. You just have to add pressure, so P1 plus 1/2. So this P1 is actually pressure, not to confuse with this lowercase p, which is density, times V squared plus P, density, GH1 equals P2 plus 1/2 density V squared plus PGH2. Now this equation is really showing the conservation of energy when we get to fluids. So if you have the equations of kinetic energy and potential energy memorized, memorizing this equation becomes much more easier. This is extremely similar to 1/2 mass times velocity squared. It's just now, remember, we don't use mass. In liquids, we use density. So this is just kinetic energy, really. Just substituting density in for mass. This looks a lot like potential energy, mass times gravity times height. But now we know that we don't use mass, we use density. So just knowing this equation is really good. So you might think, how do we apply this equation? Well, how you apply this is kind of very similar to how you apply the continuity equation, the area times velocity equals area times velocity. If you increase one of the variables or both of the variables, the other variables have to compensate. So let's take this for example. Let me draw a pipe. Okay, so we'll just say this has, this is A, this is point B, this is point C, this is point D. Now, let's try to see how the quantities change when we get to different points. So we know when we compare A and B, we learned last time that A has a bigger area and B has a smaller area, so B is going to have a greater velocity. So B's velocity is going to be great, and if we change velocity, we're actually changing the kinetic energy. So this is going to have high kinetic energy. Also, B is much more on a greater height than, let's say, C or D, right? So it's going to have a high potential energy. So what that means is, if you have, let's suppose we are holding this constant. That is how I view it. Let's say this is a constant. So if you're increasing the potential energy and we have a high kinetic energy, In order to compensate it, the pressure actually has to be low. So this is going to have low pressure. Now let me delete this. Let's look at D now. So D is, we have a high area, so it's going to have a low velocity, so it's going to have low kinetic energy. So it's going to have low kinetic energy. It's at the bottom, so D is lower than A and B, so it's going to have low potential energy. So we have low potential energy, and in order to compensate for that, the pressure is going to be much more greater. So this is going to have high amounts of pressure. So that's typically the logic that you need to solve these Bernoullis equation. Now A and C, we can go over it, but the kinetic energy is going to be high for one, and the potential energy is going to counterbalance that. So it's really hard to dictate whether pressure is going to be the lowest or highest. But for B, you're going to have the lowest pressure, and for D, you're going to have the highest pressure. Should be P, E. Okay. And this really is almost what they're talking about when they talk about the Venturi flow meter. Just real quickly, you might see this in your Kaplan book. They kind of have a tube that looks like this, and this tube that's sticking out is just trying to measure the pressure. They have this. So obviously, if you're going from a larger area, A1, to a smaller area, A2, we know our kinetic energy is going to increase. So if we increase one variable, we have to decrease the pressure. So if you look in your book, it's going to show that, this pressure bar is lower because we have a high kinetic energy, and we need to compensate it by decreasing the pressure. And the last part, 4.4, fluids and physiology. That's typically about how this might be used in the circulatory system or the respiratory system.